So what we want to look at today is to build on what we did with permutations and take it from there to start looking at some variations of different situations. One case here that we'll look at today is a situation where we are doing a permutation, but some of the objects are identical. Okay? So in this case here, we want to arrange the letters here of this word, but you'll notice some of the letters are the same. Okay? For example, we've got two T's that we're arranging. Okay? So the question is it really a permutation, a different permutation if I just switch the T's? The answer is no. Okay? We're not going to get what are known as distinguishable permutations. Okay? If something is distinguishable, that means you can tell the difference. Okay? So if we switch those T's, it's not going to make any difference. We won't be able to tell that we actually did it. Same thing with the R here and the R here. Or the O here and the O here. If we switch those, it's not going to give us a distinguishable permutation. Okay, a different arrangement. Alright, now, did we actually change something? Yes. But can we tell just by looking at it? No. Alright, and this happens a lot when you're dealing with arranging things where you have kind of categories of stuff, as we'll see later on. In our example later on, we'll see when you have categories and you don't care which one out of that category goes in that spot, you just want something from that category in the spot, then you can you have to deal with it the way we're going to see here. Okay? So you'll notice here, how many letters do we have total? 12. Okay? We have 12. So theoretically, the number of permutations would be 12 factorial. However, some of those are going to be identical to each other because we have repeated letters. Okay? So how do we get rid of those? And here's a little formula that you can use. Distinguishable permutations. In other words, we're only getting permutations that you can tell are different. Okay. So, what we would have here then is we would take the 12 factorial and we need to divide it. We need to divide it in order to get rid of those identical or repeated permutations, and this is what we're going to do. Okay? We're going to take this n factorial and this n1 and n2 and n3 and n all the way up to nk. That tells us how many of each different item there are. Okay? So, if I'm doing trigonometry here, move this down here. I'm going to have 12 factorial, but then I'm going to divide it by how many of each distinct letter there is. So,
6.
There are 2 t's, so I'm going to divide by 2 factorial. There are 2 r's, so I'm going to multiply by another 2 factorial in the denominator. I only have 1 I. Okay, now, you don't need to really put the 1 factorial in there, but to use our formula, we could. It'd be 1 factorial times, how many g's? We only have 1 g, so it would be 1 factorial. We have 2 o's, so that's going to be times 2 factorial. There's only 1 n, so times 1 factorial. We already got the o's. M, there's only 1 m, so it's times a 1 factorial. Okay. There's only 1 e, so there's another 1 factorial. We already have the t, we already have the r, and there's one y, okay? Now, as you can see, if you write out all the ones, that's a little bit tedious, okay? So, you don't need to include all the 1 factorials. What you could do is simply write it like this, and only put it over any that are repeated. Okay, so I would have 2 factorial, 2 factorial, 2 factorial, because the t's, the r's, and the o's are repeated twice each. Okay? So we have 12 factorial over 6, which is in the millions.
So if the letter was repeated 3 times, then it would be
3 factorial, yes. Okay?
Well, can't you simplify it?
Yes, yeah. Someone have what that would equal?
64.
It's 59.752.
7200, is that right?
273.
598.7520.
5200. Okay, so there's almost 60 million permutations here that we could have. Okay?
Where's the permutation, the exclamation mark?
It's under math.
You got it,
If you go to math,
No, I'm on the inspire.
probability.
Under enter, there's the question mark next to the exclamation point button.
Nope.
Yeah, on the inspire it's next to the little.
Oh, yeah.
Jackson,
There you go.
yes, like you say we cannot have the two same letters, right?
Yes.
So why there's 2 factorial, what there come from? 2 factorial.
Well, we're dividing by the 2 factorial here because with these 2 t's, if all I did was switch it, theoretically that would be a different permutation. But they're identical, so I'm not going to count that as 2 different permutations when it looks the same. Okay? So that's why we divide it by the 2 factorial, because that eliminates the repeated one. Okay? Now let's take a look at another example. Okay, it's Major League Baseball season just started. I don't know if you guys follow that much, but in baseball we have 9 players that come up to bat. Alright, so let's say that our team in the starting lineup we have 5 left-handed hitters and 4 right-handed hitters. Okay? How many permutations of left and right-handed hitters can we make for a 9-person batting order? Alright, so just to illustrate here, we could have a lefty, a righty, a lefty, a righty, a righty. How many do we have? 5 and 4? Okay. So here's another lefty, righty, lefty. Okay, so here are our 5 lefties. Wait, I have too many.
No, you.
5 lefties. Oh wait, yeah, I have it. That's right. Okay, so that could be 1 batting order. Now, we don't care who it is, we just care which side of the plate they hit from. Okay, maybe we want to mix up their pitcher, to make them have to face different ones, rather than face all the lefties in a row or something. Okay? Or mess up the outfield because they have to constantly kind of shift back and forth. So, we look at this, and we can see, how many different possibilities are there for a permutation. Not considering who this guy is, or who this guy is, just, is he a left-handed batter or a right-handed batter? Okay? So, the permutations, if we're arranging 9 people, how would we set that up initially?
9 factorial.
9 factorial, okay? That's how many ways we can arrange 9 people, okay? Now, we need to divide because we have repeats, okay? These 5 lefties are identical in our situation. So, what are we going to divide by?
5 factorial.
A 5 factorial, okay? And then for the right-handed hitters, there are 4 identical in our situation, so we're going to divide by 4 factorial. Does that make sense? Okay. Now, don't forget how to simplify. Okay? Remember to simplify, we can do 9 times 8 times 7 times 6 times 5 factorial. Here's a 5 factorial as well. And then 4, 3, 2, 1. Okay? So we can cancel out the 5 factorials. Alright? 6 is 3 times 2, so I can cancel those out. And then 4 goes into 8 twice. So this whole thing equals 9 times 2 times 7. Okay? 126 different batting lineups. And that's just by looking at left or right-handed. Okay? If we wanted to, break it down further, then out of those 126, we could, make some other decisions. All right, but those are all the possibilities. Okay. Does that make sense?
Yeah.
All right. So watch out if you've got repeated identical items that you're arranging. Okay.
Like the order is left, R, the right, left.
Yeah, left, left, right, left, right, right, left, right, left. Okay.
Is it randomly?
That's just one permutation out of these 126. Okay? We could come up with a whole bunch more. 125 more. So. Alright. The last thing I want to look at kind of the last thing. I want to just briefly review combinations, and then finally I want to kind of put some rules together with what we did yesterday. Okay? Remember, a combination, the key here is that the order does not matter. Okay? The order of our elements doesn't matter when we're doing a combination. So, notice the formula. We have n choose r equals n factorial over n minus r factorial times r factorial. Now you were given this formula earlier in the year when we did sequences and series, and we did the binomial theorem. Okay? Because we used combinations to get our binomial coefficients. But I want to make sure we understand this at this point, okay? N factorial would be what in this situation?
Your amount, like the total.
Total number of
Let's go back to it.
Total number of what things?
Possibilities.
Possible
Outcome.
Probability.
Items.
permutations, okay? Okay? Alright? That's the total permutations. I know that was a poorly worded question, so that's okay. The total permutations of all n things, okay? Now, we said today that the n minus r, we said earlier today that the n minus r eliminated the permutations of the ones we didn't want. Okay? Because we only care about the r, the first r of them, or whatever. So that n minus r factorial eliminates the permutations, just say perms for short, of the ones we don't want. Okay, so We only care about the first r of them, so the r plus 1, r plus 2, up to whatever n is. This eliminates all those permutations. Okay? So here you notice this last part of our formula, the r factorial. What that part of our formula does is eliminates permutations that have the same elements in them. Okay? It eliminates permutations that have all the same elements. Alright, so for example, we talk about arranging, let's just do a simple one. I'm going to arrange 2 of the first 4 letters of the alphabet. Okay? So I could have A, B, A, C, A, D. Oh. Okay? I could have B, A, B, C, B, D. Why do I keep writing the C? There we go. I could have CA, CB, and CD, and then I could have DA, DB, and DC. Okay? So those are all the different ways I could pick. I could arrange in order 2 of the first 4 letters of the alphabet. What this R factorial does is it eliminates, it says, okay, I've got an AB, so I don't need this BA. I've got an AC, so I don't need a CA because I don't care about order. I have an AD, so that eliminates DA. Okay? Then here's a BC, I don't need CB. Here's a BD, I don't need DB. Here's a CD, I don't need a DC. Okay? It eliminates all those permutations that have the same elements of one that we already have. Okay? You'll notice in this case, it actually cut the number in half, and that's because R, we were doing a 4, choose 2.
First half.
So R is 2, 2 factorial equals 2, so it cut the number of permutations in half. Okay? Does that make sense? So the red there is the permutations of the first 2 of the 4 letters. The blue is just the combinations. Okay? So, let's take a look at just an example of a basic combination problem, and then we're going to put some stuff together, okay? So here we have a standard poker hand. You could name any kind of card game, doesn't matter. Consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? And it makes the point of saying, and they're not always going to say this, but after the cards are dealt, the player can reorder them. All right, so the order in this case, excuse me, the order in this case doesn't matter. All right, so what are we actually calculating here?
Combination.
A combination, all right. What's N?
52.
52. What's R?
5.
5. Okay, because we have 52 and we are combining any 5 of them. Okay, you can also read this as 52 choose 5 if you remember. Okay, so again, we use our formula 52 factorial, n minus r, 52 minus 5 would be our 47 factorial, and then r factorial, okay? 5 factorial. Okay? And then we could evaluate that. And I think I remember right.
Doesn't N choose R button on the calculator?
There is one.
That is.
Where? Except if
Okay.
that's the case, we got different answers.
Well, I'm just going off of memory from like 2 hours ago,
Yeah, I
so.
got a different answer.
Yeah, you did.
What was it?
Yeah. 2,599,000.
259,896.
I can't, hang on, one person please. 2,
5, 9, 8, 9, 6, 0.
What was the,
alright. You know, I think the next one is that actually. Alright, so, you know, almost 2.6 million different hands, okay? So,
What are the chances?
alright. So, and then there's only 4 ways to get a royal flush, so that's why it's so rare.
Yeah.
Okay? A royal flush is 10 through ace all in the same suit. So, there's only 4 ways to do that out of 2.6 million, so your chances aren't really good. So,
Isn't that James Bond movie? He's getting royal flushes every single time. You know?
so when you know you're cheating. Okay? Alright,
Yes.
okay. Any questions? Questions about just using the combination? Alright. Now,
LeBron gets royal.
here's where we start to combine things together. Alright? We're combining 2 ideas. One, if we read the problem, we're forming a 12-member swim team for 10 girls and 15 boys. So that's how many we're choosing from. Okay? The team must consist of 5 girls and 7 boys. How many different 12-member teams are possible? Okay? So now think about it. What are we going to have to use? Before you do anything with the numbers, just think. What are we going to have to use here?
combination?
Combinations.
Repeated permutation.
I mean, you're not gonna have to be.
We aren't going to have any repeated permutations.
Maybe 2 separate
2 separate
combinations.
combinations. Okay, one for the girls and one for the boys. Okay, so what's the combination for the girls?
10 choose 5.
10 choose 5. And how about for the boys? 15 choose 7. Okay, we want to pick 5 out of the 10 girls and 7 out of the 15 boys. So, what do we do with those then?
Can you add them?
Times together.
What do you guys think?
Or multiply
it's
them?
multiply
We take the
Why
two
would we
numbers.
multiply? What is that called?
It's
Association with
well, in bio we just call it multiplication.
Yeah, some people call it that. What did we learn it was called yesterday? The fundamental counting principle, okay? We have multiple events. And guys, this is something I know you're used to thinking in terms of an event being something happening, okay? But you have to have a much broader definition of that when you're talking about counting principles. Events are just, in this case, picking a girl for the team and picking a boy for a team. Okay? Those are events. So, event 1 is the girls, picking the girls, and event 2 is picking the boys. Okay? So, remember we used M for the number of ways that the first event could happen. And this would be the number of ways that second event could happen. Okay? So we then multiply those together. And by the way, doing this together actually can make it much easier to evaluate. Alright? Take this as far as you can by hand. Okay? You should have an integer. Well, you shouldn't have any more denominator by the time you're done. Okay? So take it as far as you can by hand using the formula. Alright? And we're going to put it all into 1. So
I'll do
10 factorial over, what's this going to be? 10 factorial over 5 factorial times 5 factorial. And then that's going to be times,
Wait, why times 5 factorial?
because 10 minus 5 is 5, and then 5 is 5.
Yeah, but why 10 minus 5?
For combinations, remember we just looked at
Okay,
n minus
okay.
r and the r.
Okay.
Okay? Then what goes over here?
15 factorial.
252 is the first one.
Okay?
8 factorial, 7 factorial.
Alright. So, practice simplifying your factorials. Get it down, cancel out the whole denominator and see what's left.
252 is the first one.
You already showed us that.
Oh, yeah, it is the one from the problem.
Okay? Write them out, cancel out common factors until your denominator is completely canceled out.
That's the right answer.
Okay? Okay. Now, when you get to this point, the easiest way I think to cancel things out is start with your biggest numbers in the numerator. Okay? I've got a 15 up here. Well, a 15 is 3 times 5. So I'm going to cross that out and cross out the 3 and a 5 on the bottom. Okay? 14 is 2 times 7, right?
Yeah.
So there's a 14, there's a 7, and a 2. Okay? 13's prime, it's not going to cancel out. 12 is 4 times 3, and since all of this is multiplication, I can cancel out the 12 and that 4 and that 3. Okay? Because it's all multiplication everywhere, so I can cancel across. 11's prime, there are no 11's on the bottom to cancel it with. Here's a 10, and I've got a 5 and a 2 still over here, so I can cancel those out.
There's the 6 and 6.
Okay?
Wait, you can.
Because this is multiplication, yes.
You can do 6 and 6.
Okay? Yeah, now you can look for identical ones. Here's a 6 and a 6.
And the 4 with the 8.
Anything left?
4 and 8.
Okay, yeah, there's a 4. We can cancel that out, and that would leave a 2. Alright, so you'll notice this reduces quite a bit. We just have 10 times 9 times 2 times 7 times 13 times 11 times 9. Okay? And that one should come out to that, right?
Yeah.
There we go. I knew that number stuck out in my head for some reason. Okay? Now, even if you got something where you had bigger numbers like this, okay, you should be able to do it by hand, alright? You all learned how to multiply numbers like this back in like 3rd grade, so you should be all set.
So we should add a non-calculator.
Okay.
Test.
So then on the non-calculator portion, I'm not gonna hear any whining when you get like something up in the hundreds of thousands,
Wait, you're really
right?
gonna make us do like 10 times 9 times 2 times 7 times 13 times 11 times 9?
Sure.
That's not fun.
Sure, but here's the thing, guys, make your life easier, okay? Don't just blindly go straight across, alright? Use some of, we talked about how to multiply a 2-digit number by 11, right? So let's do the 9 times 7 is 63. And then how do you multiply 63 by 11?
You add the 2 and you keep them.
Yeah, 6 and 3 is 9, put that in the middle, so it's 693. And now you've got the 7, 11, and 9 taken care of. Okay?
How should you do that?
You wanna check?
77.
63 times 11. You add these together, that's 9, and you stick it in the middle
Oh wow.
of the original number.
What I would do is 7 times 11, 77, and you multiply by 10.
Say I have
7.
Here's the thing, guys.
You take out 7.
Just figure it out, okay? Just do the multiplication, alright? You've got, 2 times 13 is 26. 26 times 10, you have 260. And you've got another 9 that you got to deal with, okay? But still, I mean, you got 3-digit numbers, all right? So it shouldn't be too terribly difficult, okay?
But you can't do that.
No,
So.
It's like at least 6 more.
All right. So that's all for the new stuff. When you're looking at a problem, make sure you ask yourself those questions that I've said that you need to consider, okay? Ask yourself, are these items repeating, okay? If I'm selecting things out of them, am I replacing them? For a permutation and a combination, we are not replacing the thing after we pick it out, okay? If I was picking, cards out of a deck and I was replacing it every time, it would just be 52 times 52 times 52, however many times I picked it out. But a permutation or a combination is selecting it out without replacement, okay? So keep that in mind. All right, now, I gave you a number of problems to try. 43 to 51 are somewhat basic. Okay, there's not a whole lot that you have to think about in terms of the situation. Although here we do have repeated letters. Okay, when you get down to 59 through 74, all right, you need to look at the situation and ask yourself, does order matter? Okay. Should I use a permutation or a combination? So for example, on 59, it's a U.S. Senate Committee on Indian Affairs, has 14 members, and we're trying to select the committee. So does order matter? No, because it's just a committee. We don't have specific positions within the committee. All right, so you've got to think about that. Even if something might be put in order originally, doesn't matter what order you're selecting them in. For example, on number 60, you're picking 12 questions out of 14 on an exam. Okay? You can choose any 12. Doesn't matter what order you pick them in. No. you still pick the same questions, whether you chose 1, then 16, then 5, or you chose 1, then 5, then 16. It's still the same questions in the
There's
end.
only 14 questions.
Alright, or whatever it was, yeah. So, but anyways, look at the situation, and guys, practice, practice, practice. I gave you a lot of these for a reason, okay? If you don't get down the counting aspect of this, then when we get to the probability aspect, you're not even gonna have a chance, alright? You've gotta get this down here, before we start throwing in the probability aspect of it, okay? Alright.
Do you want to look at this?